So it's my pleasure to introduce Kari Lock Morgan, who will give the final plenary presentation of the conference. Kari earned her bachelor's degree at Williams College, earned her PhD in statistics at Harvard University. She's a faculty member in the Department of Statistics at Penn State University, right here. And Kari is a textbook author, as many of you know, along with other Locks. And she is also a frequent presenter at workshops and conferences, especially presenting on topics of teaching statistics related to simulation-based inference and multivariable thinking. And Kari's title, as you can see, is directly relevant to our conference theme. She'll be talking about helping introductory students to evaluate evidence. So thanks very much for coming, Kari. We look forward to your presentation.
Okay, thanks, Alan, and hi, everyone. I'm Kari Lock Morgan, as Alan said, and I'm excited to be here. So when Alan invited me to give this talk, the email said, well, it should relate to the conference theme of evaluating evidence, and it should be accessible to people who only teach introductory students. So hence, a title was born. So I'm going to talk about teaching introductory students how to evaluate evidence, kind of taking these ideas we've heard throughout the conference and bringing them to an introductory course. So let's split the title into two pieces for a second and give credit where credit's due. So in terms of teaching introductory students, a lot of my thinking here has been very much influenced by my parents, Robin and Patty Lock, who most of you know, they're sitting in the back there, but also really the entire stat ed community. And by that, I mean you, all of you. So I just wanted to take this moment to say thank you all for being so friendly, so welcoming, so thought-provoking, as we've seen throughout this conference, and really such an inspiring community to be a part of. So thank you. In terms of evaluating evidence, that's been a pretty separate piece of my career until now. So my thinking there has been very much influenced by my PhD advisor at Harvard, Don Rubin, who many of you know pioneered a lot of the work in causal inference, and there the entire causal inference community. So I want to be very upfront. There's different kinds of evidence. Today I'm going to be talking explicitly about how to evaluate, causal evidence in particular, which I know isn't everything, but I only have one talk to give, so that's what I'm going to talk about. All right, so let's take everything an expert needs to know about evaluating evidence, throw this giant, vast mountain of knowledge into a big funnel. And what pops out of that tiny little end at the bottom, at the beginning, that's what an introductory student needs to know about evaluating evidence. And I think that's a really important image to have in mind whenever we're talking about intro stat. There's so many things. This is important, and this is important, and this is important. And yes, it's all important for evaluating evidence, but we're not talking about teaching students everything that's important. We're talking about what is really most crucially, fundamentally, absolutely necessary for every single student to know about evaluating evidence. So I know we may have different opinions here. I'm going to take this talk to share my thoughts on this question, but then the breakout session to follow will open this up for more collaborative discussion, maybe even some debate, so you're welcome to come share your thoughts there afterward. All right, so in one slide, what do I think every introductory student should know and understand about evaluating evidence? Well, just to set the stage, suppose we're comparing A versus B, and I'll give context to this in a second, but A and B could be two different treatment groups, two levels of an explanatory variable. Pick your favorite example. In our sample, let's suppose the A group has better outcomes than the B group. What are the possible explanations? Well, it could be that A really does cause better outcomes than B. That's the causal claim that we're trying to evaluate evidence for. But there are other possible explanations, and I know Dennis mentioned this earlier. We have to be considering those alternative explanations. So one alternative explanation maybe the groups differed at baseline. And maybe it's nothing to do with A versus B, but those baseline differences that are driving the better outcomes. Or maybe it's just random chance. Right, and yes, there are many, many other possible explanations, but I think, when I think of what pops out at the bottom of the funnel, for me, these are the three things I want every student to consider every time they're evaluating evidence. So this means that if you want to evaluate evidence for number one, for that causal claim, you have to evaluate evidence against groups differing at baseline and against just random chance. So we have to be preparing our students to do that in an intelligent way. So this is a coherent framework, I think, that might help put it all together under the umbrella of evaluating evidence for students and might help them remember to kind of check all these explanations. But for this audience, what do I think our students really need to know? Confounding and basic ideas of inference. So at this point, I'm going to pause and acknowledge what maybe many of you in the room might be thinking. So yeah, obviously I teach confounding and inference in my intro stat course, and out comes your smartphone and you tune out for the rest of the hour. And yes, right, I understand. I know that all of us teach confounding and inference. That's not anything new here. But to steal the phrase of USCOTS 2 years ago, show me the data. Let's look at some data here. So this is data, not data yet, but questions from the goals and outcomes associated with learning statistics assessment out of the StatEd group at the University of Minnesota. And I've just picked out 2 learning objectives here specifically that relate to confounding. I'll talk about inference on the next slide. But just to get us all together, raise your hand if you teach intro stat or have ever taught intro stat. So all of us, right? You wouldn't be sitting here if not. Oh, keep your hand up. Sorry, I should have said. So keep your hand up if you cover at least one of these learning objectives in your intro stat course. So no hands went down. Nobody. So we all cover this. Keep your hand up if you think most of your students understand at least one of these at the end of your course. At least one. All our hands are still up. Okay. What about both of these? Keep your hands up. So about half went down. Okay. All right. So let's see what the data tell us. All right, so first of all, I want to give a shout out. I don't think he's here at this conference, but Bob Delmas very generously shared the most recent data as of last week with me, so these are up-to-date numbers. Okay, so able to reason about the purpose of random assignment, 27%. Able to reason about how correlation does not imply causation. So to steal a phrase from Holly Lynn earlier, it ain't there. And I'm going to make it even worse if you can believe it. So this question, these are multiple choice questions. This question has 3 options. This question has 4 options. In both cases, our students are significantly worse than random guessing. So chickens pecking away at a keyboard, they do better than our introductory students. This is the low point of the talk, I'll just say. It can only get better from here, right? All right, so that's confounding. What about inference? Are we doing any better there? Well, we certainly should be. We spend however much time in our introductory courses on the topic of inference. And this is certainly not all of inference. I specifically called out p-values here, talking about evaluating evidence, but there are other questions. So there's 3 here. But Ron actually made my job a little easier. We can go ahead and cross off that one. We're not going to say statistically significant anymore. Maybe, I don't know. But we're going to suppose. But there's still 2 left. So we're going to do the same thing. Raise your hand if you cover at least one of the remaining 2 in your introductory course. So all of us, right? Yeah. Raise your hand if you think your students understand at least one of these at the end of your course. Keep your hand up if you think your students understand at least one. So all of us, good, I didn't know if you'd become more skeptical after the last slide. And keep your hand up if you think your students understand both of the remaining objectives. Interesting. Danny Kaplan, the one sole hand remaining. Was that right, or were you just the slowest to put your hand down? Okay, great. All right, so able to reason that a smaller p-value provides stronger evidence against the null. So this is not, I know we heard a lot about the bright line being bad. This is not the bright line. This is the most fundamental, I think, property of a p-value. Smaller is more evidence against the null. So we're doing better than confounding, but still half of our students aren't getting that a smaller p-value means stronger evidence against the null. Able to reason about an incorrect I guess I'll just give you that number so in case you're curious. Able to reason about an incorrect interpretation of a p-value. In particular, these are students who think it's okay to say that a p-value is the probability that the treatment is more effective. Half of our students. So half of our students, so there are subtle misinterpretations of a p-value. This is not one of them. This is the backwards it's the opposite of direction of how a p-value should work. And half of our students think this is okay. And there were only 2 choices to this question. So we're not doing very well. And again, I'm going to take a guess at what's going on in your heads. So yes, these numbers are really bad, but maybe that's not surprising. There are a lot of, quite frankly, really bad statistics instructors out there. There's a lot of people who are stuck teaching these courses, who don't want to be there, who don't care, who have never seen the GAZE guidelines, never want to see the GAZE guidelines. Maybe this isn't a surprise. But who gives their students nationally recognized pre-post assessments of conceptual understanding? We do, us here in this room. So if anything, these are probably maybe upper bounds for what's actually going on. So I'm not saying this to put a damper on this otherwise really inspirational, joyful mood that USCOTS always is, but rather as a wake-up call to all of us that yes, we're all teaching confounding. Yes, we're all teaching inference, but our students aren't getting it. So maybe we have to be thinking about how to modernize how we're teaching these topics. So again, I'm going to give my thoughts on some ideas for how to do this the rest of this talk. If you have your own ideas, which I'm sure you do, that'll be the second half of the breakout session, is more collaborative thinking on how to improve teaching here. Okay, so I like to start my classes with a real scientific question of the day and then use data to try to answer that. That's my way of getting at what Ido Gall so correctly, I think, called out as needing to focus more on context. So we're going to start here with a real question of the day. Our question for today: does eating organic improve your health? It's relevant. It's something I think all of us might be wondering. So let's evaluate the evidence. All right, so we're going to look at 2 data sets. I'm going to start with a data set that I think most of you are familiar with, the National Health and Nutrition Examination Survey. It's a large national random sample. And the last time they asked about organic was a decade ago, so this data is a little bit old, but it's what we have. And our sample size here, there's about 5,000 people with data on the questions we care about. All right, so our treatment or explanatory variable: in the past 30 days, did you buy any food that had the word organic on the package? So yes, this is a very liberal definition of eating organic, but even so, only 36% of people said yes. And this number may be different now. Again, this is a decade old at this point. So that's organic. Our response or outcome variable is self-reported with all the biases that has. Yes, I admit it, but again, it's what we have. Self-reported general health status. Would you say your health in general is excellent, very good, good, fair, or poor? And this is a little bit hard for intro students to work with, so we're just going to collapse it into a dichotomous outcome, 2 categories. So about 36% of people have very good or say they have very good or excellent health. The real question, of course, what happens when you take this and break it down by the different organic statuses? So here's the data. Among those who bought organic, about 46% say they have very good or excellent health, as compared with only 33% in the non-organic sample, for difference proportions of 0.129. So in our sample, people who bought organic are healthier. That's what we just saw. What are some possible explanations? Well, maybe eating organic really does improve longevity. But what else? Maybe the groups differed at baseline, and maybe it was just random chance. So I'm going to talk about random chance more later in the talk in Inference. But for now, I can just say it got the lowest p-value R will give. This is not just random chance. And I know we're not supposed to use bright line thinking, but I think even in a world beyond p less than 0.05, I think we can all agree that p less than 2 in 10 quadrillion probably lets us rule out random chance. And I don't think Ron's here. I was going to ask him if he's okay with this, but I'm just going to go out on a limb and say probably. Okay, so it's not just random chance, but what about groups differing at baseline? So we have a whole bunch of people who bought organic. We have a whole bunch of people who didn't buy organic. What do you think? Do you think there might be some differences there? Of course there are differences. Anyone want to shout out some options? Money, yeah, so that's one of the most obvious ones. So organic food is expensive. people who buy organic, not surprisingly, are richer. Here's income versus organic. So people who buy organic are richer. Richer people are, not surprisingly, healthier. Okay? So this is showing the income distribution by health status. I'm just gonna flip it around because we really want the health status by income. So this is a little bit of a non-standard plot, but stick with me for a second. So the x-axis here is income. The NHANES actually categorizes income, so I'm using the categories as by NHANES, but if you wanted to just do your own binning like you would for a histogram, that works just as well. But within these categories, the y-axis is giving the proportion of people in that category with very good or excellent health. And the bubble size is kind of superfluous, but it's the size of the people in that category, the number of people in that category, so the denominator for the proportion. You can see the exact same thing. As people get richer, their probability of having very good or excellent health goes up, not surprisingly. So nothing new here so far, but I think, at least for me, the magic really happens when we put these two together. So people who buy organic are richer, and richer people are healthier. Therefore, it should be no surprise that if you take a group of people who are richer, shift them over here on the income axis, of course they're gonna be healthier, even if organic has no benefits whatsoever, just by the virtue of this baseline difference in income. And that's really the key point that I think all students have to be able to really deeply understand. And I think one way of doing it is through the use of visualization like this. And these are not fancy visualizations, but it's going beyond two variables with visualization. And I have to say, not all visualizations are created equal. So this plot down here is kind of weird. If I had just done the standard 2x2 box plot or side-by-side box plots, I don't think it would have really made the same point. So sometimes you have to be thoughtful about how to visualize your data to best illustrate the points you want to convey to your students. But that's you being thoughtful, not necessarily your students. And I think it's something that we can all do. But that brings me to the first of my three Asians. So this is really cheesy and really corny, I admit it, but I wanted you all to have something very tangible and concrete that you can not only take back with you today, but actually remember 3 months from now when you start to go prepping your classes for the fall. So my stab at that is by the use of the three Asians. And the first of the three Asians is, anyone want to guess what I just did? Visualization, yeah. I think the more we can be infusing our courses with visualization, the better for our students. I think really a picture does speak louder than words, to use a cliche phrase. But also, I've talked about this before, but I think visualization is the most accessible way to bring ideas of multivariable thinking into our intro classes. And if you want to get an issue like confounding, you have to bring issues of multivariable thinking into your intro courses. Okay, so I'll leave you guys speculating for a little while on what the other two Asians might be. You can kind of let that percolate for a bit. But let's go back to our slide here. So we did find that the groups did differ at baseline. So we have two possible explanations. What does that mean? It means that we really can't determine causal evidence here. We can't cross off number two, so we have no way of knowing whether it's one or two or both of them together. All right, I think that's a really important point for students. If there's more than one possible explanation, you can't choose between them. But equally important is that we can't rule it out. Just because there's an alternative explanation doesn't mean that organic can't make you healthier. It just means we have two possible explanations here. And I think I really like this framework because we're not talking about rejecting or failing to reject the null. We're just saying, hey, there's multiple possible explanations. Okay? All right, so just making this point, I'm sure all of you make this, but if you try to directly compare groups that are not comparable to begin with, they differ at baseline, you really can't get causal evidence, and the results can be quite misleading. So what do we do if groups differ at baseline? Well, this is the topic that a lot of causal inference tries to address, and most of it is much, 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 much higher up in the funnel and nothing that drops down to intro stat. But the one thing I think we maybe can be doing more in intro stat is trying to look within similar groups, where I say similar just on one baseline confounding variable. I think that can be accessible to introductory students, not because I want them to be able to grapple with causality in the presence of baseline differences, but because I think it's yet another way of helping them understand this really important concept of confounding. So here we're just going to look within those income categories. It's the exact same plot I already showed you, except broken down by organic or not. And actually here, even within groups of similar incomes, people who bought organic are still healthier. So do we have evidence that eating organic makes you healthier? It's not income. Or it's not solely income, I should say. Anyone? Danny's shaking his head no. No, of course not. There's a million other confounding variables. We adjusted for one here. So I could have picked almost anything, but people who buy organic are more likely to always have green vegetables on hand. They're less likely to smoke. They're just more likely to engage in healthy behavior in general, et cetera, et cetera, et cetera. The list could go on and on and on. There's differences on many, many, many measured variables, and even more dangerously, differences on countless unmeasured variables, and that's the piece that we're never going to be able to fix. So we're going to turn to randomization in a second, but let me just back up for a minute and say, a given time, I'm just showing you one example, but ideally students would see multiple examples of this over the course of their class, including something that pertains to common sense, so people can intuitively reason. People who buy organic are richer people are healthier, that makes common sense. Something where the baseline difference shifts the effect like we saw here. This will be almost all real examples fall into this category. But I think it's also important for students to see something a little more extreme where the baseline difference actually reverses the effect. You do that plot where you look within baseline subgroups and all of a sudden the effect reverses. So pick your favorite Simpson's paradox example. I still remember the first Simpson's paradox example I saw in my intro stat course 20 years ago from my father. And I think the learning that happened as I tried to grapple with how could this possibly be true went a long way toward helping me understand confounding. Maybe something where the baseline difference masks the true effect. We don't talk about that much, but it's just as likely. And something where the baseline difference creates a false effect. Creates something out of nothing. And this could be, it looks like there's an effect, then you look within subgroups and it goes away. But you can also artificially concoct such an example. So one way of doing this is to take the real data set that we've been working with, but simulate organic or your treatment based only on income, only on the confounder. So the details here can go kind of under the hood. The students don't need to know all of this. But use, say, logistic regression to predict a person's probability of buying organic based only on their income, and then flip a biased coin for whether they actually fake bought organic or not. Most important for students to walk away with is that these simulated values are based only on income. They're fake. They have no basis in actual organic purchases whatsoever. So they cannot have any real causal effect on health by the way that they're simulated. But lo and behold, when you look at these fake values in health, there still is a higher health proportions in the fake organic group. Not as much higher, but still higher. And it's actually a significant difference, even though we're not supposed to say that. So this significant difference pops out, we now know by design, solely due to the baseline difference in income. So just another way of helping students realize that baseline differences can give you results that are completely spurious, as the book Alan just gave away mentioned. And here, if you look within income, as we would expect, the difference goes away entirely because it was based only on income. Okay, so this is a problem. Simply observing data just as it is will almost always result in these differences, which is a problem we just saw. So how do we alleviate this? I certainly don't need to tell all of you this, but of course, we randomize treatment assignment. And by virtue of the randomization, baseline differences should be minimal, by definition, just due to random chance, and this would therefore allow for causal conclusions. All right, so that brings me to the second of the three Asians. So randomization, I think, is absolutely crucial to statistics. I think one important thing is it allows for causal evidence, but it's also, it can be used as the foundation for inference. And I think both of those, I think randomization deserves to stay as a cornerstone topic in our introductory courses. All right, so one approach would be to just tell students, hey, if you randomly divide groups, they should be pretty similar. That's what that's what most of us probably do. But another approach would be to actually convince them that's true by, again, simulation. So we can simulate a randomly assigned version of organic, this time not based on income, not based on anything, but just random assignment, just flip a coin. So we have the organic data set here and just this appended, just permuted version, just randomly assigned organic. And then when you look within these randomly assigned treatment groups, of course, we don't see baseline differences anymore. The groups should look pretty similar at baseline just by virtue of the randomization. So here's income, pretty much the same. Whether or not they smoke, pretty much the same. Whether or not they always have green vegetables on hand, pretty much the same, et cetera, et cetera. And I actually give this to my students in a lab very early on in the course. We haven't talked about inference or randomization distributions or anything yet, but I have them simulate one random assignment and go off and look at the relationship between that and a bunch of other previous confounders and kind of verify for themselves the power of randomization. So take home here, without randomization, groups will differ at baseline, so it's really hard to get causal evidence. With randomization, the groups should look pretty similar at baseline, which then allows for causal evidence. And I want students to walk away with, you can't ever check for all baseline differences. It's impossible because you don't have data on a lot of them. But you can always check for random assignment. And that's kind of the take-home message for students when evaluating evidence. If you want to know if the groups differ at baseline, the best evidence against this is the use of random assignment to treatment groups. So when evaluating evidence, students should always be asking, was there random assignment? Okay. So I say this is the best evidence. Of course, you can go even beyond this, and you can try to do better than pure random chance. And I think this could be sufficient for an intro course, but depending on your students, you might want to get in a little bit more design principles, such as the idea of randomizing within similar groups. So blocking, you might want to randomize within matched pairs, where the pairs are as similar as possible, or maybe even identical. These are my boys, Cal and Axel Lock Morgan. They're in the back there with their sisters, Daisy and Zinnia. So hi, guys. And they're wearing, if you can't see it, treatment and control group shirts, randomly assigned, of course. And I think they have to hold a record. They're 6 now, and this is their 4th USCOTS, so I don't think anyone can beat that USCOTS to age ratio. All right, anyway. All right, so let's take a step back and think about this in terms of pedagogy for a little bit. So a lot of you may be thinking, why do I keep saying this phrase, groups differ at baseline? Why not just call it confounding, as we've always done? And I have several reasons. I actually thought very intentionally about how to say this. First of all, let me approach why baseline, and this very much comes from my background in causal inference. But for causal evidence, you really need this temporal relationship. There has to be a time when the treatment starts, and some point after that in time, a time when the outcomes are measured. Everything that's measured pre-treatment is what I'm referring to as baseline. And in terms of these variables, groups really do have to be similar if you want to make causal conclusions. But there's also a whole bunch of variables that can be measured post-treatment. And there, the treatment groups very well may differ due to the treatment itself. And that's okay. We shouldn't be trying to adjust that away. So I think that's an important distinction to make when we're talking about similar groups. So that's why baseline, but why groups at all? So I used to, and as I'm guessing a lot of you do, teach confounding through scatter plots and through correlation. And I think it's fine to do that. But I think the idea of group differences is a little more tangible and concrete than just the abstract idea of confounding. But I think more importantly for me, the idea of group differences translates more directly into evaluating evidence, where you're often comparing groups for a causal effect. And I think even more directly, it translates into the benefits of randomization. We almost always have randomization into treatment groups, not some quantitative explanatory variable. So I think there's reasons to be thinking about focusing on groups. Yes, it's just a special case of confounding, and yes, you can still call it confounding, but I think we might think more about group differences. So to summarize my thoughts about confounding in general, This does require multivariable thinking, as is pointed out in the most recent edition of the GAZE guidelines. We should be doing this in our intro courses. We have to help students reason in the presence of a third variable. And no, I don't think we have to go beyond 3 in intro, but I think we do have to go beyond 2 to that third variable. This seems like it should go without saying, but I'm definitely guilty of not using data in the past when I've taught confounding. So of saying, here's a bivariate relationship, there's this other common sense intuitive confounding variable, so of course that's going to mess things up, but without ever actually showing data on that confounder, or even having data on that confounder. So I think explicit use of multivariable data sets to convey multivariable thinking is crucial. And some of the benefits that allows us to then ideally thoughtfully, explicitly visualize that confounding for students, which I think can really help, and also this idea of showing the data broken down by similar groups within the confounder. So that's multivariable thinking. Random assignment is important. All of us know that. I don't need to tell you that. It's not just about study design. I think when a lot of us cover it, it gets stuck in the study design portion of the course, which is okay. It's good to think about purposeful data collection, but it has to continue throughout the rest of the course. Every time students are evaluating evidence, they should be thinking about confounding and random assignment, in my opinion. And lastly, I think simulation can really help understanding. So I'm going to be talking more later about simulation-based inference, but you've already seen 2 cases in which I've used simulation completely separate from inference. And I think we can start to use it more throughout our introductory courses. Which brings me to the third Asian. I kind of just give it away. But the third Asian is simulation. And I think throughout our courses, this can really be helpful as a tool to take really abstract concepts and make them very concrete, much more tangible for the students. They can get their hands on, is this random assignment actually yielding baseline differences or not? There, so there you have it. Those are the 3 Asians: visualization, randomization, and simulation. All right. Okay, so I'm going to turn my attention now to random chance, and for that I'm going to introduce a different data set. So this is working with fruit flies. We had fruit flies randomly divided, and students now know the crucial importance of that word, into 2 groups of 500 flies each. One group was fed organic food, the other group was fed conventional food. They used 4 different foods. I'm going to focus here on the potato data. They measured longevity, fertility, stress resistance, activity. I'm going to focus on longevity here. Oh, I meant to ask, are there any high school teachers left in the room? Raise your hand. Okay, awesome. So it's kind of a fun fact. This study was actually done by a high school student for a science project, and it went on to get published in PLOS One and get picked up all over the media and everything. But it's kind of a fun success story that high school research can actually be very meaningful and impactful. So let's just jump to the data. So this is longevity by whether, so number of days survived by whether or not the particular fruit fly was fed organic potatoes or conventional. And the organic fruit flies lived about 3.5 days longer on average, which is actually quite a bit in the lifespan of a fruit fly, so it matters. So again, in our sample, the fruit flies who ate organic lived longer. You can see where I'm going with this, I bet. What are the possible explanations? And I want students to kind of just do this over and over again. So one possible explanation, eating organic really does increase longevity. Other possible explanations, maybe the groups differed at baseline, and maybe it's just random chance. So here, I already told you that they used random assignment in the study. We can go ahead and cross out groups differing at baseline. Also, they're fruit flies, so I'm not sure how different they can be, but they use random assignment just to be sure. But what about just random chance? So to me, this begs the question, what kind of results would we see just by random chance if there were no difference? Organic and conventional didn't matter at all. So given my middle name and maiden name of Lock, I think many of you will not be surprised to hear me say, we can simulate to find out. So just before I go on, can I see a show of hands? Who is already using some form of simulation-based inference in their introductory statistics courses? Okay, great. So a lot of you, I'm going to go relatively fast through this part, although not too fast because not every hand went up. All right, so what do I mean by simulating random chance? So here's a subset of the data. I did not purposefully put up all 1,000 data values, but you get the idea. So we're first going to start by assuming no difference whatsoever. So the number of days each fruit fly survived over here is going to stay the same regardless of whether they fed organic or conventional potatoes. Then we're just going to mimic random chance. So we're just going to re-randomize all the fruit flies into 2 different treatment groups, again of size 500 each. So we're going to take all those treatment labels, scramble them up, redeal them out, just re-randomizing into treatment groups. I then just calculate the statistic that we were working with originally. Here we're doing the difference in means. You could do any statistic you want. The process is exactly the same. And then do this thousands of times. But that's really all the intuition you need. So we're doing this thousands of times. You can do this in almost any software package now. I'm going to show StatKey because we designed it with pedagogy and specifically introductory students in mind, but pick your favorite software. It's not software specific. Can I do this while holding a microphone? We're going to see. All right, so we're going to go into a test for a difference in means. I'm going to upload the data file. So it says organic flies file. And longevity is my outcome. Organic is my response. Okay. So now when I click generate one sample, I'm just repeating what you just saw on the PowerPoints. I'm just re-randomizing the flies into treatment groups. I'm getting a difference in means, which is right here, and plotting that sorry, I can't see on here, negative 0.6, and plotting that with a dot on the distribution. The whole point was to not do this one time, but to turn to technology to do this thousands of times. So I'll do it just a couple thousand times here. Here we go. So this idea, I think the simulating random chance is relatively intuitive to students, but this idea of a distribution of a statistic is not necessarily something that comes easily. It's fundamental to inference if we go about doing frequentist inference, which maybe John would say this is the problem, but it's not an intuitive concept. So you might do, like Jane said, and have students actually compute their own statistics and add their own statistics to a class distribution first. But I think it also helps for technology to aid in this understanding. So I really like that you can see the original sample, you can see each simulated sample, and as you hover over the distribution, as you hover over each dot, you can see that each dot came from an entire simulated sample, which I think helps reinforce that really quite difficult concept. But why are we doing this in the first place? We wanted to see whether you might see this observed statistic, 3.4, just by random chance. Do you see it anywhere? I don't know if you can see the axes, but it goes from about -2 to 2 on here. So 3.4 isn't anywhere on this distribution. I've simulated about 11,000 samples now, nothing anywhere near 3.4. Just to make it a little more explicit, I can pull up this editable right tail box, enter in our observed statistic of 3.4, and get that a little bit more of a compelling visual of it, just way, way, way out in the tail, where it's very, very, very unlikely to see this just by chance. Okay. All right, so when we go back to our slide, we'd already crossed off groups differing at baseline because of random assignment. Here we can now also cross off just random chance. We simulated 11,000, didn't get any statistics anywhere near as extreme as the observed. So what are we left with? We have pretty convincing evidence that eating organic really does increase longevity in fruit flies. So what's the take-home message of my talk? Eat organic, yeah, right. Well, if you're a fruit fly, so no, really. What is kind of the take-home message? And I'm not going to conclude yet, but at least from here, this is not everything I think introductory students need to know about evaluating evidence. I couldn't cover all of that in an hour, but if we can get them really understanding this framework and reasoning about the different possible explanations, I think that would really go a long way toward helping them intelligently evaluate evidence. Okay, so I finished my example. We've made our conclusion. We're done really answering our organic question. Did anyone notice the omission of something kind of big or small in this case? Oh, okay. So yeah, there might be other variables. Yeah. I don't know if gender of fruit flies matters, but maybe. But yeah.
I don't know if
Okay, yeah. But even if that's the reason, that could still be a reason to buy organic if the health benefits come from fresher. But anyway, sorry, I wasn't actually looking for scientific things. So I don't want to. We can talk about it later if you want. But thank you for your thoughts. But what I was actually talking about is a p-value. So thank you for your intelligent insights. But it's not exactly where I was intending to go. But yeah. So I just did the whole thing and never even mentioned a p-value or calculated a p-value. So I really think that students need to see and really deeply understand the concept of a p-value. I can get behind this no bright line thinking, but I think we need to have, not just because it's everywhere in the literature, but I think our field needs some kind of formalization of just by random chance. But I don't think we have to start there, or even should start there. And I think maybe a way of kind of easing us away from this bright line thinking might be to start with really extreme examples. Either the statistic is way out in the tail, it's never gonna happen just by chance, or it's smack in the middle of that distribution, and yeah, that could easily happen just by chance. Examples where you don't need any formal calculation. There is no number to calculate because you can just see it with your naked eyes. And if you don't have to calculate a p-value, even more importantly, you don't need an exact threshold. It becomes not even an issue. You don't have to say, well, is this low enough? Because obviously it's low enough, or obviously it's not low enough. And get students really comfortable with this idea of just, would I see a result this extreme just by chance? And then once they get that, because that's what I want them to be thinking about, not the numeric value of the p-value, once they get that, then the p-value, I think, is a very natural way to quantify this intuitive concept that they've already been thinking about. And then from a randomization test, it's actually really easy to get there. So if the null is true, so we're assuming no difference, assuming the null is true when we're doing the simulation, that's where the distribution is centered around. Just by random chance, we're mimicking that re-randomization into treatment groups, that's the random chance. The observed statistic, so I made this up because the real observed statistic is like over at the dessert room, but just let's say it was 1.6. It's the actual observed statistic they're used to working with, not some standardized version. The chance of obtaining a statistic as extreme, in this case, in all cases, it's as concrete as simply the proportion of dots in the tail. There are 5 dots out here, I simulated 1,000, the p-value is 5 out of 1,000. It's so much easier than the area under a theoretical density distribution in the tail beyond a standardized test statistic. It's much more concrete for our students. And I think, to me, this concept really epitomizes the 3 Asians. It's very visual. Students can see what will happen just by chance. They can see how extreme their observed statistic is. And it's completely based on randomization and made possible via simulation. Okay, so if you're not already convinced, what are some other reasons I think we might want to consider moving more towards this approach? For me, I could stop here. It's directly connected to the key concepts, done. Everything else is just kind of icing on the cake for me. It's the same process for many statistics. This really reduces the cognitive load on the students, but also makes it more generalizable to new situations. It's more flexible. You can plug in your own statistic if you want. John will like that. If you want to use a random n, sure, go ahead and use a random n. You can make it match the data collection however you would like. There's fewer conditions. So for a randomization test, there are no sample size or distributional requirements whatsoever. So not only is it more applicable, but you don't have to spend all that class time harping on conditions over and over again. Nobody likes doing that. It has better connection with data collection. I think this was a lot of George Cobb's original motivation for suggesting this. Less reliance on prerequisite knowledge. So students who come in weaker in algebra, you don't need it as much. All that probability theory, random variables, theoretical density curves. Maybe that's important in later classes, but you don't need students to understand it to understand the concepts of inference here. So it's more directly accessible to more students. Promotes better understanding? Well, let's evaluate the evidence. All right, so I'm not the first one to do this, but I'm gonna show data from a recent transition we made here at Penn State, since you're all here in Happy Valley. So these are scores on the goals post-test. So the goals was the same assessment I showed at the beginning. So we first made this transition in our introductory biostatistics course. I'm just gonna, right off the bat, say this is the national average, this horizontal line at 47%. This is a hard test, so that's our benchmark. But you can see Comparing traditional to SBI, the SBI students on average scored almost 19 percentage points higher on average. So talk about a meaningful effect size, here you go. Due to the really good success here, we rolled it out over a general everybody take it intro stat course and saw not quite as dramatic, but still 11 percentage points higher on average in the SBI group. So Dennis, you said, if you want convincing evidence, just show me the data. Well, here it is. I think this kind of speaks for itself, but I'll dig a little deeper since this is the talk about evaluating evidence. So in our sample, the students who had SBI have higher goal scores. What are the possible explanations? And this is supposed to be redundant by this point. So maybe SBI really is better for conceptual understander, but maybe the groups differed at baseline and maybe it's just random chance. So it's not just random chance, but what about groups differing at baseline? We did not use random assignment here. So we can look at pretest scores as one measure of baseline differences, and it looks pretty similar between the two groups. The treatment group is 0.2 of a point higher, but that's not going to explain the kind of differences that we saw. But just to be sure, I went through and I used propensity score matching to create groups that were very similar on all the measured baseline variables we had data on, which were actually quite a few. And even after matching these similar groups, we still saw a post-test difference of about 11 percentage points higher in the SBI group. So that's balancing on students. What about instructors? So we're going to use one of the same tricks we saw earlier in the talk. We're going to look within instructors, within similar subgroups. So there's 2 instructors that had data, both traditional and SBI. So we can make comparisons within instructors. And for both of them, we're seeing the same kinds of effect sizes. Still around 12, this is 12 percentage points different, still right around 11 percentage points different. So however you look at this data, you're still getting the same general idea. So what else? And I almost left this slide out because this is not an exhaustive list of everything else you ever might want to know, but some other things that have come up over the course of the conference or that I think are worth mentioning. So there's been a lot of discussion here about a meaningful effect size, and I've noticed in conversations some people mean the estimate, some people mean the standardized effect size, so I'm just going to give both. So this is the introductory biostatistics results and introductory statistics. The difference in means is clearly very meaningful. It has practical benefit. There's the confidence intervals. I'm not going to go there in this talk, but simulation can also really help with understanding of confidence intervals. The standardized effect size, Jessica, I added that in on Thursday, on Friday morning, just for you after your talk. So 1 here and 0.76. The What Works Clearinghouse for research and educational interventions defines a meaningful effect size as 0.25. So we're quadruple or triple it here, depending on the course. So yes, that's another bright line that we have to be wary of. But it really is a meaningful effect size here. Something that we kind of sweep under the rug in Introstat, which I'm worried about sweeping under the rug, is missing data. And here, I think missing data, especially in the form of differential attrition, is dangerous. Here, this would only make our results stronger, I think, if we accounted for it, but it's something we have to be cognizant of. And lastly, replication. So there's been a lot of talk about this at the conference by a lot of really great speakers. Maybe this is the 4th Asian, I don't know. But let's look at replication. So we already saw replication within Penn State alone. So we saw biostatistics and intro statistics. We saw the same semester, different instructors, same instructor, different semesters. We saw that for 2 different instructors. But I'm not the only one who has looked at the effectiveness of simulation-based inference. So one study out of Iowa State actually used random assignment. They randomized students into courses, and they did this really cool design where they had 2 instructors co-teach the course, and they alternated who taught which class to mitigate the instructor effect. So they found that SBI improved conceptual understanding. Beth Chance and co-authors, they have a really large data set, which I think is really exciting. It's multi-institutional. It covers lots of different SBI curricula and traditional curricula. They found better scores with simulation-based inference. Nate Tintel and co-authors looked at students' pre-ability coming into the course and the effects of SBI, and found that regardless of your ability coming into the course, SBI gave better scores, et cetera. The general theme is that all of these find better conceptual understanding with SBI. So I went kind of quickly through that, but you can read the papers if you're interested. So let me stop for a second. Where's Danny Kaplan? So Danny, I'm gonna use your star system here. So let's look at his star system. So our effect size is bigger than the smallest effect worth mentionable. We get a star. We adjusted for baseline variables explicitly in the Penn State data via the matching. That gives us 2 stars. Our effect size has practical benefit, definitely. That gives us 3 stars. Random assignment, they use random assignment at Iowa State. That gives us 4 stars. Replication by independent researchers. Here's at least 3 different groups who have used completely different students, different curricula, different assessments, different institutions, and all are finding kind of the same message that SBI improves conceptual understanding. Is that a fair assessment of your star system? I don't want to put you on the spot, but yeah. So I gave you one framework, but I think this also should be brought into introductory statistics courses. I wrote this talk before seeing Danny's, but I think it's a great way to think about evidence. And I think based on the Amazon stars, we have really compelling evidence that we should be teaching with simulation-based inference. All right, so to kind of summarize, because I want to leave a couple of minutes for questions. So I've given this framework that I think all introductory students, when they're evaluating evidence, should consider. Not necessarily in this framework, but consider these options. So if we find better outcomes in group A than group B in our sample, students should think through at least 3 possible explanations. The causal explanation, but also the possibility that groups may have differed at baseline, and also the possibility of just random chance. And if we really want our students to evaluate evidence for a causal claim, they have to know how to evaluate evidence against baseline differences and just random chance. And I think it's our job as statistics educators to be doing what we can to help students reason intelligently about number 2 and about number 3. How do I think we can do a better job with that? Any guesses? The 3 Asians, there you go. So I think the more we can be infusing our courses with visualization, ideas of randomization and simulation really throughout, I think that can only help our students, in my opinion. So thank you very much, and I think there's time for questions, but I'll let Alan take that over.
Thanks. Thank you very much. You can tell Kari and I both like to have the handheld mic, but I'll be gracious and give it back. And I'll use this one that I don't like as well. Any questions for Kari? Lots of chance to ask questions in the breakout, but we do have time for 1 or 2 now.
Yeah, Jim. Oh, sorry.
Can you rule out the possible confounding effect that anybody involved in the study is enthusiastic for the new method?
So that was exactly the point of the within instructor comparison at Penn State. So yes, I agree. When we're first transitioning over and comparing a pilot section, the instructor that volunteers to teach the new innovative pilot section may be different than the instructors who don't. But once we rolled it out across all sections and all instructors were teaching with that, those are the instructors that you're looking at with the within instructor comparison. So I think that part was crucial for that against that argument.
Done.
It is possible that the instructors were more enthusiastic for simulation-based inference.
And if that's the case, and if that's part of the causal mechanism, great. If it makes the instructors more enthusiastic and they therefore bring that enthusiasm to their students, that's fine with me. I guess, but these were not the instructors who initially like were gung-ho about it. Like, not that they were against it, but these are people that after we rolled it out across everyone. But yeah, that's a good point. Yeah. So the question was about DAGs, and do I think DAGs should, directed acyclic graphs should be included in an introductory course? So I include one kind of pseudo DAG in my course. I have a picture of here's the explanatory variable, here's the outcome or response variable, here's the confounding variable, and I talk about how the confounding variable is affecting both of those. We care about the relationship from the explanatory to the response. what does randomization do? It breaks the relationship between the confounding and the explanatory. So I kind of do a little picture like that, but I don't do any formalization of it at all in my courses. Not to say you can't, but that's not the route that I've taken.
One more question?
What does assessment look like for you of that content for your students?
So I still give pencil and paper exams. I tried to do it in a computer lab at a previous institution, and I was just too worried about cheating, quite frankly. It was just too much of a problem. So they don't have any technology during exams. So I give them pictures of, say, here is a randomization distribution without any shading on it, and students need to know to go and look for the observed statistic, circle the proportion in the tail, or count the number of dots in the tail, if you will, and make an intelligent interpretation based on that result. For example, also all the conceptual questions, like if you increase sample size, what do you expect to happen? Like things like that.
What about the difference in baseline?
Yeah, so I asked them about like what, I'm trying to think if I've explicitly shown a graph. So I definitely have a million assessment questions that say, can you conclude causality here? Did they use random assignment? Usually I'm not even explicitly directing them to say, did they use random assignment? They have to know to check, did they use random assignment? I don't think that I've explicitly shown the visualizations of confounding on an exam, but I definitely expect them to look for random assignment. They might have to think about what might a confounder be in this situation. Sorry, I misinterpreted your question at the beginning.
Thanks very much. Thanks again.